Welcome everyone to the last talk of the day. So we're delighted to have Jason Hartline tell us about dashboard mechanisms for online markets.
Thank you. So I want to just let you know, so my co-author, Aleck Johnsen, is a PhD student at Northwestern. Denis is a professor in economics at UVA. Zihe Wang is a computer scientist who's at the Shanghai University of Finance and Economics. And Onno Zoeter is the head of data science at Booking.com. This is a project that we started while Aleck, Denis, and I were visiting Onno at Booking.com. And then Zihe spent a quarter visiting Northwestern and was able to prove some theorems we couldn't prove ourselves, which was awesome. This is a brand new paper. And one of the reasons why I want to speak about it here is because you guys are really awesome at proving theorems too. And there's some pretty hard theorems that we got stuck on and weren't able to finish. And so maybe some of you guys can pick these up and finish it. Good. So I want to just, I didn't get the memo from Yuval about not having motivation. So I apologize to everyone who likes to just start with the equations. I'm going to have a little bit of motivation. And my motivation is, the greater motivation is it'd be really excellent if computer science theory could help us understand computation that are happening all over the place in the world, not just in digital computers. And the big challenge of computation that happens all over the place in the world is to guide that computation, you can't just tell everything what to do. They're going to be basically operating for themselves. And so the computational primitive is local, individual, or strategic computation. And you can sort of guide it by setting up the payoffs, but that's what you have to work with. Okay? And you want to make this local, individual, or strategic optimization achieve good global outcomes. I think a very important key application area is what I like to call online markets, and I take that term very broadly to be places where interactions between individuals are mediated by some market mechanism which chooses the outcomes based on some rules. For an observation I have, which this is topic area that theoretical computer scientists have been studying for around 20 years, and there's a lot of excellent work here. But there's a twist on it that I think is super important that people haven't been talking about too much, which is most of these environments don't allow what's called truthful mechanisms, where the agents have a very simple strategic choice of just submitting their true preferences, and then the mechanism does everything else magically. So most mechanisms don't have that property, and there isn't actually a very well-developed theory for mechanisms that don't have this property. So that's sort of the space of this talk. So I want to start with some basic assumptions of online markets. They're prevalent in a lot of them. And you can think online advertising if you want, but actually almost all of them have this very same property. Okay? That is, one property is long-lived agents with persistent values. So if you're thinking about advertisers in these auctions, their value per click doesn't really change all that frequently compared to how fast the auctions happen. Okay, probably if you knew what the values the advertisers had, you'd probably have a pretty good algorithm for assigning which ads go where. Okay, so given the values of the advertisers, which are these V1 through Vn, you would have some algorithm which I'll call X, which decides how much clicks an advertiser gets. Okay, and probably this X is monotone. So if some advertiser has a higher value, you'd give them more clicks. Okay, probably this environment has a lot of randomization in it. It's probably stochastic. So probably the amount of clicks someone gets as you increase their value is a random variable that's going to be increasing with the value. So I'll think of the number of clicks as a number between 0 and 1, which is a probability, and it'll be a strictly increasing function. Okay, in many of these environments, they're sort of standard, what I call non-truthful payment rules, and I think the most fundamental of these is winner pays bid. So you say how much you want to pay per bid, click, and you get a click, you pay that amount. Okay, that's sort of the most standard, and this is, I think, the most pervasive mechanism there is. Okay, so here's the basic question that we're going to be talking about in this talk, and that is, I'd like to know if there's a winner plays bid mechanism, I'll call X tilde if it takes bids, that implements the desired algorithm that I had in mind on values for all values you could have in equilibrium. Okay, so in other words, when people have these values, there's going to be some equilibrium in some implementation I have that I hope gives me the same outcome as X would on the original values. That's what I would hope. I want to basically get the outcome that I want in equilibrium.
So X is 0 or 1?
X is going to be a probability between 0 or 1 for each player.
Real quick, what's a non-truthful payment?
Like winner pays bid. Okay, so if I always charge you your bid when you win, you're never going to bid your value because then you get 0 utility for that.
Right.
So you're always going to shade your value down and give me a non-truthful bid. Okay, so that's my basic setting. I think this kind of scenario applies a lot, and so we're going to try to see what we can do in this kind of a scenario. Okay, I want to give you some context and then say sort of at a high level what the results are going to be. So some context, looking at winners pays bid auctions, is a literature on price of anarchy that looks at simple auction rules like highest bid wins, winner pays bid. Right, so that's also known as the first price auction if you have one item, which has been studied a lot. And if the agents are substitutes, for example, if you have some number of items to sell and you could sell each one to any agent, that's agents are substitutes, you end up getting constant price of anarchy bounds, things like E over E minus 1, 1.58 as your price of anarchy bounds. If the agents are complements, meaning you can sell to this couple agents or to this couple agents, but you can't sell to one of these guys and one of these guys, so the agents sort of complement each other. Then you end up getting linear bounds in the number of agents in terms of your approximation factor. Okay, I actually view all of these as impractical. Okay, so losing 1.58 fraction of the welfare or revenue is not practical. Losing a linear amount of the welfare is not practical. So I want to actually look at getting essentially p-TAS style results. I want to get within epsilon of the optimal revenue or welfare. Okay, so here are some results. So I'm going to be talking about a general framework for answering this kind of a question. Again, from my previous slide, you have some mechanism, some algorithm X you'd love to implement. I'm going to show you how to implement that when you can. Okay, and so those of you who know about the VCG mechanism, it's a framework kind of like the VCG framework. A bunch of my results will be about Nash implementation, meaning I want to implement the thing in Nash equilibrium, so full information equilibrium. And in particular, I'm going to show that for multi-unit environments, I have a bunch of units to sell, and I can sell one unit to to any agent. Then for allocation rules to look kind of like proportional weights. So think about a single item environment. If I map values to weights and then I assign the winner with probability proportional to their weight, okay, that would be proportional weights allocation rule. So for multi-unit environments and X is proportional weights, you can implement those in Nash equilibrium. And this is sort of a starting point for us, but I want you to think of it as like soft max. So I want to assign the item to the player with the highest value. Instead, I'm going to do a soft max. I'm going to do like highest value minus the entropy regularizer, and that would be like exponential weights. Exponential weights is a special case of proportional weights. So that would be within our result. Okay? I think more generally, substitutes like a matroid feasibility constraint that many of you have thought about before, that's an open question, so I'd love to see people thinking about that question. And you can imagine like what would proportional weights mean for matroids. You can come up with reasonable definitions of that and ask whether you can Nash implement that. Okay? And then for complements, again, so the simplest setting is I have two players. I can serve, I either serve both of them, or I can serve this one other player. In that environment, you can't implement things like proportional weights, which would mean map player 1 and 2's values to weights. If the sum of those weights over the total weight, you allocate to them. Otherwise, you allocate to the third player. Okay, so those you cannot implement.
So one, the general framework is not a Nash implementation. I didn't understand the relation between 1 and 2.
Yeah, so this is, they're not, it's not orthogonal. This is, you'll see two kinds of implementations. One is Nash equilibrium, and the other one is what I call persuadable agents. Okay, so what are my general frameworks? One of the general frameworks is this Nash implementation general framework, where you can take a social choice rule, and if it looks like proportional weights, you can implement it. If it's complements, you can't. Like, that's the kind of result you have for that. And then for what I call persuadable agents, which is a new model that we think is relevant for online markets, you can implement any monotone continuous social choice function, X. So any algorithm you have that's continuous, so stochastic environment that'll make it continuous, you can implement it. Okay? So that's an overview. We'll see if it's not clear what that means right now. We're going to be going in detail into what these mean. I just wanted to sort of say sort of where we're going beforehand. Okay, Nash implementation. So the basic question of Nash implementation is there a winner pays bid mechanism X tilde that takes bids and implements the algorithm, the outcome you want, X, in Nash equilibrium for all values? Okay? In particular, the question is, for what X does such an implementation exist? Okay, so let's have just some definitions before we get into it. So agents have values. We already said that, V1 through Vn. A winner pays bid mechanism looks like the following. You give it a bunch of bids from the agents, and it's going to compute for each player that own that player's allocation, which think of as a probability that they win or not, so between 0 and 1. And then a bidder is going to pay when they win. So if they win with probability xi of b, then they pay their bid when they win. So the expected payment is bi of xi of b. Okay, and their utility is they basically get their value minus their bid when they win. Okay, so good. I'm talking about Nash equilibrium. And so this is a little bit strange because in Nash equilibrium, everything is known. But I want to parameterize actually all of the Nash equilibrium as a function of the valuation profile, which everyone knows. Okay? So I'm going to write the Nash as a function of the valuation profile, and I'm going to let this beta function be basically the bid function, which takes valuation profiles and says what everyone is going to play for that valuation profile. Okay? And so this function beta, the bid function, is a Nash equilibrium for all values v if, for those values v, the bid for player I is his best bid for his utility function, given that other players are playing by the bid function. Okay? And then x tilde implements x if x of v is equal to x tilde of b of v. Good. So I'm going to be talking a lot about proportional weights. And again, as I said, I want you to think single item environment. So I can basically, the x is always summed to 1. So think single item environment for all the talk. So xi is summed to 1. And you can choose what those xi's are. Proportional weight says I first map values to weights, and then I select winner with probability proportional to the weight. Okay, one reason why I like this family is a very general family of mechanisms, so you get to pick the weight function, is that regularized maximization looks like this. And the theory I'm going to be talking about is going to require continuous functions, and so I can't just use max. Okay, but I want to think about maximizing welfare, and I can put like a regularizer on that with a very small coefficient, and I can get almost exactly the true maximum. Yeah.
I'm going to back up a second. Is your question about taking truthful x and finding x tilde for them? It's about mapping truthful allocations to winner pays bid allocations?
So again,
I think you said x of v.
x tilde
Yeah.
implements x. So x is what I'm given. I have an algorithm that if I knew the values, I would want to run that algorithm.
Oh, okay, it's an algorithm.
Okay? Now I don't know the values, and I have to have a mechanism that's going to get bids.
Sure.
So x tilde is my mechanism that gets bids. And I would love it for be the case that when people found Nash equilibria, for all values where they found the Nash equilibria, then I ran that x tilde mechanism, I just get the thing I wanted.
Yeah, I missed that x was an algorithm. Got it.
So in your definition of implements, do you mean there exists a Nash? There exists a beta?
I'm going to mean for all. Okay? So I want uniqueness of this Nash equilibrium, which I didn't write here, but yeah.
Just to make sure that I understand, in the definition of beta, in the Argmax, should it be beta minus I of v rather than v minus I?
Yes, absolutely. I'm sorry about that. Yeah. Yeah, so v is a function, beta is a function that requires all of the values to know it. So absolutely, that should be a v. Thank you. Okay, so the main idea that is used in both parts of this talk is that I want to combine the inference that comes from econometrics in economics, which is looking at bids and figuring out what people were thinking when they gave you those bids. So economic inference with trying to implement some outcome. And I want to just walk through a simple example, which is not going to be what I want to do, but it'll give you an idea for how you could possibly do this. Okay, so here's an example, 2 agents, and I want to think about just instead of starting with x, let's just start from some x tilde, some bid allocation rule. And my bid allocation rule is just proportional bids. Okay, so what does that mean? So player 1 should win with probability b1 over b1 plus b2 for 2 players. So just proportional bids. This is actually a standard mechanism that's studied in the literature. Okay, and so I want to point out that if you give me equilibrium bids, that each bidder's first order condition, looking at their optimization problem, is going to tell you what their value was. Okay, so I can like reverse engineer what players were thinking, what their value was when they submit these bids. Let's just walk through how that works. Okay, so agent 1 with value v1 chooses b1 to be this argmax, right? Where this is the probability that they would win with any bid b, given b2 is, player 2 is bidding b2. Okay, and notice that when we're doing an after-the-fact analysis like we're doing right now, we know what b2 is, because player 2 bid b2, so we see it. Okay, so equilibrium must satisfy the first order condition, which I've taken the thing and differentiated it, right? And I've actually done that differentiation for you and figured out what it is, and it's this function. Okay, so you tell me what the bids were. Hey, they were 1 and 2. Well, now I can tell you, using this function, that v1 is 5 halves. I can also tell you what v2 is. I didn't bother to write that down. Okay, so after the fact, I know what the values are when I run this mechanism. So here's the thing. Well, now I'm sad, right? Because I wanted to allocate efficiently. Instead, I ran this b1 over this mechanism, which didn't allocate efficiently, right? We sometimes allocated to the player with a lower value, right? But I know the values, and so now I'm sad. Why didn't I just give it to the guy whose value was v1?
But something I didn't say, it's not a Bayes Nash equilibrium. So
Nope, Nash.
So it's
Not Bayes Nash.
So
Nash.
how does one bidder, when he makes his bid, know? I mean, is there the other bid to be Nash?
That's what a Nash equilibrium is. So remember, we're in full information, so players both know their values.
Yes. But in how do they submit the bids? I mean, is there some order that they submit?
I guess
the
you
bids?
should imagine they are playing repeatedly and
No.
usually they
Look, we're just talking about Nash equilibrium.
Right.
And when we talk about Nash equilibrium, we never talk about how we found the Nash equilibrium. We just talk about what the Nash equilibrium is. Okay? So there's a whole other literature about how to find it, which actually I will address in the next part of the talk. But for now, let's assume we're there. Okay? Good. So in hindsight, our mechanism knows the values exactly. Well, what I really want is I want to use this idea to, well, if I know the values in hindsight, why didn't I just do a good thing in the first place? So that's what I want to do. Okay, so so this was a little bit complicated how I solved for bids, etc. So I want to make it much simpler on the next slide. Okay, so this is a standard theorem about equilibrium in these single-dimensional environments. Usually it's written for Bayes-Nash equilibrium or dominant strategy equilibrium. It also applies to Nash exactly the way I've written it here. It's pretty much the same. Okay, so a mechanism x tilde and bid function b is in, it should be Nash equilibrium, not Bayes-Nash. Sorry, I cut and paste from slides. And I'm going to just let x of v here equal the combination. Okay, if this x is monotone in each coordinate, so xi is monotone in coordinate I, vi, and the payment identity, which is the payment to the player, satisfies this formula. Okay, and usually this additive term at the end is 0. And I just want to draw geometrically what this payment identity says. So here's some increasing xi of vi. This first term is this area vi times x of v, right? This integral is the area underneath the curve. So obviously the payment is this area above the curve. The difference between those two. So geometrically that's what it is. Good. So the thing I'm going to use about this to basically, this lets me solve for equilibrium in winner pays bids auctions very succinctly because I have two equations for payments. The payment identity gives me one equation for payment in terms of the allocation rule that I want, right? And the winners pays bid gives me another equation for payments. Payments have to be bid times allocation, right? You pay your bid when you win. Good, so I can use that to solve for what the bids have to be. So if you tell me the allocation rule x, I'm just going to tell you, well, the bids have to be integrate the thing, do this equation, that function, divided by the probability that the player wins. Okay? Good. So, if you told me now the x you wanted, I know exactly what bid function can be the only bid function that implements that x. I already know what the equilibrium has to be in a winner pays bid auction. So here's the idea. Let's just set x of b, x tilde of b, equal to x of b inverse of beta inverse of b. Just do that. Two issues. This bid function might not be one-to-one. There might be multiple inverses. Another issue is when I define a game, the action spaces need to be a product space, right? So everyone can bid in some range. They can bid in some range, and the image of beta might not be a product space, right? So the inverse might have points I can't invert because they aren't even in the space. Okay. Turns out this is actually a pretty easy problem to fix. Problem 2, not a big deal. You can basically find close enough points to give something reasonable for everything, but no one's going to bid those anyway in equilibrium. They're always going to bid a real point. So it just needs some consistent way of making sure people don't bid those weird points. Okay, you can see the paper for that. This inverse is the main thing that I want to talk about. Okay, and this is where some serious math is needed, and even more serious math is needed, is identifying when these functions are one-to-one. Okay, and let's just go back a slide to look at the function we're talking about. So beta is payment, which is this function divided by xi. So we're talking about when is, for what x's, mapping from Rn to 0, 1 to the n, is this crazy function one-to-one? Okay. So here's a cool proposition actually. If there exists a winner pays bid mechanism for x, if and only if beta is 1-to-1, it might be pretty obvious to some of you now why that's true. Good. Here's a cool theorem. Beta is 1-to-1 if the Jacobian of beta is positive definite. I'm not going to go into that. It's a famous theorem in this space. So all right, so we look at proportional weights for multi-unit environments. So again, think single item, think proportional weights. So each player has a monotone function mapping values to weights, and then I get these weights and I give it to player I with probability wi over the sum of the other players' weights. Okay, so the Jacobian is positive definite, and you can compute the inverse efficiently. Which means I can implement this thing I want to implement for any proportional weight social choice function. Okay, cool. Complements, beta is not 1-to-1. So I can apply the backwards direction of my only if to say I can't implement these. Okay, and that's because I can't choose, like, well, there are two sets of values that map to the same bid. I see only the bids. I can't know which ones the values are. And if I choose the wrong one, now the players are like, but that wasn't the equilibrium, right? So it's not the right thing. Cool. Coming back to Yuval's question. I want to change gears. So that was my Nash equilibrium stuff. Hopefully you can see what the math questions are there. I'm going to come back to them, the open questions at the end of the talk. Here are some challenges. One challenge, Yuval. Agents have to find this crazy Nash equilibrium. How can they possibly find that, right? Another challenge is I can't Nash implement general allocation rules X. I can only do special ones. Like I can't do complements, but that kind of sucks, right? So I might like to be able to implement far more things than my Nash implementation allowed me to do. Okay, so here is an idea that we ripped right out of what actually happens in the industry in online markets. Okay, you give the bidders a dashboard that helps them understand what the counterfactuals are, meaning what would happen if they put in different bids than what the bids they currently are putting in. So you as the platform come up with these estimates that help bidders know what the bid landscape looks like. And all they have to do is read off that thing and figure out what is the best bid for their utility function.
How truthful are these dashboards?
Huh?
How truthful are these dashboards?
Well, we'll talk about that. Great, good point. So I'm going to call agents persuadable if they will follow the dashboard, if following the dashboard converges to best response. Meaning the dashboard can be wrong, maybe initially when it doesn't know too much, but it better eventually be right. Okay, so you can't get people to just believe in BS. You have to actually, it has to be a good strategy to follow the dashboard. But if you're wrong initially when you don't know stuff, maybe the agents are happy thinking that you know more than they do, and it's better than they would have come up with on their own.
So does the output of my dashboard depend on your interacting with your dashboard?
No, these are individual dashboards. But they might be based on history, where you learned something. So anyway, so here's a dashboard mechanism. It's given by two things. One is the dashboard, which is a per agent bid allocation rule. And the other is the bid allocation rule, which is mapping a profile of bids to an outcome. So these are different mathematical objects, which I tried to make sure was clear here. The dashboard takes each player and tells you from their bid what's the probability of winning. And the bid allocation rule maps a profile of bids to who wins. Okay, and here is my historical values dashboard mechanism, which I think is the one that makes the most sense. Publish a bidding dashboard with the bid allocation rule from historical estimates of values. So I'm assuming you as the principal have an historical estimate of values. Why am I assuming that? Well, in step 3, you estimate values. So maybe you ran this before and have estimates from before. Okay, I want to solicit bids. And I'm going to assume their best response bids to my dashboard. Well, now I just know what the values are. So now I just plug those values directly into my original social choice function, my original algorithm that I want to implement, and I run my algorithm on the true values, or these estimated values. Okay, and I charge the winners their bids as usual in a winner pays bid mechanism. Okay, and these results are just like super straightforward. If you have a monotone continuous algorithm, then in this mechanism, following the dashboard converges to best response in 2 rounds. The first round, you have no idea what's going on because you don't have any estimates. In the second round, you know the true values, and so you post the true, the the Y tildes are actually the true allocation rule for the true values in the next round. And now we're basically in Nash. Okay, so in 2 rounds, we're in Nash. Okay, and so I say any monotone continuous algorithm can be implemented for persuadable agents by a dashboard mechanism. So this is just a really good idea. Online markets should publish a dashboard, should assume agents best respond to them, and should then know the true information and optimize for the true information. But then publish the dashboard that corresponds to the true information. So you don't try to fool the agents. You give them the best information you have, which is what you were trying to output.
But if an agent feels he has better information than the dashboard, he would deviate.
That's correct.
Would that then
That'd be a
disturb
great
the
question to study still. I don't know what would
destroy the correctness of the dashboard in the second round?
if they don't believe the dashboard, then whatever. So this is one of the reasons why. So I actually presented this talk in the opposite order that we conceived of this stuff. We think this is the right mechanism, but this is not a Nash. So when is this the same as a Nash? Well, when X is like proportional weights, and you can just do the Nash implementation before and have this sort of the feedback loop in there, okay? And so I think it's pretty robust for settings like proportional weights with a single item or multi-units. It's not going to be so robust like that for complements. Okay. I want to talk about some connections to the literature, which I think are important here. So one connection to literature is implementation theory, which is this general question of what kinds of functions X can we, algorithms X can we implement in equilibrium. Okay, this is a great survey by Jackson to look up that. So that basically this literature characterizes X where there's a unique equilibrium. Essentially the characterization is any monotone X is implementable, kind of like my dashboard result. However, the mechanisms that come out of this literature are crazy, impractical mechanisms that you would never want to ever use, whereas this dashboard is a realistic looking thing. Okay, and in particular, there are sequential mechanisms where you interact a couple rounds. In one of the rounds, there's cross-reporting, so you ask the agents, like agent 1, to report what they think agent 2's value is, and so in full information, they know. And then they do some kind of like shooting the agents if they disagree. Like if agent 1 and agent 3 disagree on agent 2's value, you just kind of like blow up the world, right? So that's what these mechanisms do in implementation theory. And so sort of our take on that is to get rid of these kind of ridiculous mechanisms, you want to restrict the space you look for. So like these winner pays bids mechanisms where you get bids, you can compute any outcome you want, but winners pay their bids. What can you implement with those simple kinds of rules? And there we gave a characterization of you need the Jacobian of the bid function, and you need to understand what that means for the X, and we gave sort of a partial answer for that for proportional weights. The other thing I think is interesting is information design, otherwise known as Bayesian persuasion. And this is an awesome area of the people in economics are especially excited about. Basically, the agent has a prior, and they need to make a decision. The prior states the world making a decision to optimize their utility. There's an informed principal who knows more than the agent does, but wants the agent to make a different possible decision. Right? So the principal can give the agent a signal, which then the agent updates their prior and will make a different decision than they would have before. So how can a principal convince an agent to do what the principal wants and not what the agent wants? Okay? Good. So our suggestion here is we have something kind of like persuasion. We give a dashboard. Agents do what they want based on the dashboard. But we have a more relaxed model, which allows the principal to be wrong at first, but just be and learn over time, but just be having more information than the agent does. And basically you can't persuade the agent of something that's not true eventually. But as long as the principal is right eventually, you can persuade the agent. So I think it's a more sort of amenable to learning, amenable to CS ideas model that's in the information design space. So I think that might be interesting much more broadly. Cool.
Side payments? Could the principal pay the agents to follow his?
Not in that literature. No, that literature is the only thing you have is you can give them a signal which is correlated with the true state.
Okay, but in your model, which you're free to change? Would you want to put in side payments?
In my model, there are already payments, which are you pay your bid. Now, if you have side payments, why don't I just screw that and have like a second price rule? You have to be careful how you ask the question. Okay, and again, coming back to this, coming back to the first comment of implementation theory, one of the things that we got more meaningful mechanisms by restricting the space of mechanisms to something that's sort of natural. So I'm nervous about letting it go all over the place. Okay, so again, my context, I just want to come back to what I said my results were now that we have seen what the details are. So I'd like to have a much more meaningful characterization of what's implementable besides just saying proportional weights, which seems like a broad family, but it's not everything in that space. I think that we should be able to implement social choice rules like in matroid environments that say are smooth versions, sorry, a soft max for like matroid environments. I think that's an open question. So we study proportional weights with complements. And I'm not saying there isn't something there that you can do for complements, but I don't know what it is. Okay. All right. Thanks for your attention.
Any additional questions?
So what does your dashboard mechanism do in the first round when it has no information?
Yeah, so I'll give you two answers. It doesn't matter. Any monotone function gives the result that I say you converge in 2 rounds. But I think a much more relevant answer is there is no first round in online mechanisms. It's not like you turned Google search ads on day 1 and then that was it, right? So imagine instead you're running a mechanism and some new bidder shows up. But you actually could probably estimate for whatever bid they put in what probability they would win, because you actually have all the data from whatever bid would happen, what they would do. So when a new bidder shows up in an on-running mechanism, you could give them the right dashboard on day 1 for them, actually.
But there's no large market assumption in your work.
No.
Is Booking.com doing something different?
I have no idea.
And even if he did, he would tell you the same thing.
Yeah.
So for different auction mechanisms, your bid function would change and your payment function would change, but do the conditions for implementation stay the same? Like,
Okay, so you could ask, so I was talking about implementation with winner pays bid rules, right? You can imagine implementation with like GSP, right? Or you can imagine implementation with all pay bid rules. Okay, so one thing I actually don't like about our theorems is they're very specific to winner pays bid, whereas I'm sure that the same thing holds for all pay, right? But our analysis wasn't the right analysis that was flexible enough. And in fact, I'd like to have a reduction. I'd like to have a theorem that says proportional values works, and if some function works, then putting in any monotone weights instead of values works also. Right? I'd like to have a composition theorem about that instead, and I think that would actually be a good step to getting things like all pay for free from an analysis of first price. For things like GSP, I want to. That's hard to talk about because doing the revenue equivalence calculation of what payment characterization are, you can't do that. That characterization I did on the first slide when I talked about winner pays bid auctions. You can't do that for GSP. But one thing you can do is if you look at our dashboard mechanisms, so what I know about the Google dashboard for ad auctions is they just give you a cost per click curve. Right? They say you pay this much, you get this many clicks. That's actually a winner pays bid information. So even though the auction is GSP, they give you winner pays bid information, and then they just say, well, what bid is it that gets that cost per click? And then you can put that bid in, and that would be your GSP bid, right? So, if you publish your dashboard as winner pays bid, and then there's a language that maps those bids into bids that you would actually put in, that's then sufficient to implement these dashboard mechanisms. And so it doesn't really matter.